Have you ever wanted to fly like these snow geese? Glue some feathers to your arms and flap off to exotic places? I'm Carl Adams, and filming birds is my passion. It takes a lot more than feathers to fly like a bird. You also need remarkable eyesight, incredible coordination, prodigious power, a light, stiff skeleton, and real wings, not arms. Let's see what makes a bird a bird.
I'm Alan Gubanek, retired faculty member from the University of Nevada, Reno, where I taught biology for 35 years. And I've been fascinated by birds since I was a kid. Do you know that there are over 9,000 species of birds? Here are some types that you'll probably recognize.
Perching species include robins, jays, and finches, birds we often see in yards and parks. These are flickers. Perching birds have claw-like toes. Swimming species include ducks and geese. They have webbed toes. Shorebirds include herons and avocets. They have long legs and necks. Predatory birds include hawks and owls. They have sharp talons.
All birds look different, yet they're all amazingly similar. That's because they're all designed for flight, even some who don't fly. We'll focus on those things that are common to birds.
How are birds' bodies different from ours? Bird bodies come in different sizes, but most are shaped like teardrops, compact and streamlined.
Birds are warm-blooded animals with backbones, like us. Unlike us, they have no teeth or lips, and they have bones in their tongues. Their beaks are covered with keratin, a tough protein that also makes our fingernails. Both upper and lower parts of the beak can move, allowing birds to open wide.
Watch this hooded merganser. You can tell what birds eat by their beaks. This eagle has a meat hook. These pelicans have fish grabbers. House finches have seed crushers.
Birds have remarkable eyesight. Their eyes are much like ours, with lenses, pupils, and retinas. Their eyes are larger relative to their body size than ours and mostly hidden inside their skulls. They see better than we do, and some birds have eyes as sharp as telescopes. They all see color, and most see ultraviolet light, which we can't.
Birds' eyes are flatter than ours and don't rotate much in their sockets. They turn their heads instead of their eyeballs. They also have 3 eyelids, top, bottom, and one that closes sideways. Hunting birds' eyes face forward. Others have eyes on the side. Birds hear through small holes in their skulls, located behind their eyes and covered with feathers. Their inner ears and hearing range are roughly similar to ours. Birds are very sensitive to tone and rhythm changes, allowing these Canada geese to recognize family members, even in noisy flocks.
Birds' brains are relatively large for their body size, but they're quite different from ours. Because they rely heavily on vision, they have large portions of the brain devoted to vision and coordination. We're learners and problem solvers. Birds, however, inherit most of their knowledge and behavior patterns as instincts. But they also learn with experience, things like eating different foods, or better hunting and fishing skills, like this night heron. Birds can't quickly alter their inherited behavior patterns, and sudden changes in their environments can destroy entire populations.
We mammals carry our babies inside until they're born, but this could make birds too heavy to fly. They lay hard-shelled eggs and keep them warm until they hatch. Some birds are ready to run, swim, and find their own food when they hatch. Others are blind and helpless. Their parents protect and feed them for weeks. Above all else, birds are feathered flying machines, designed for high power and low weight. Tiny, ruby-throated hummingbirds fly 500 miles across the Gulf of Mexico, flapping their wings hundreds of times per minute for 20 hours. Bar-headed geese migrate over the Himalayas at altitudes of 28,000 feet. Bar-tailed godwits fly 7,000 miles from Alaska to New Zealand, crossing the Pacific in 7 days without stopping. How do birds get enough energy to fly? Energy's produced in individual cells, especially in wing muscles during flight. Circulating blood brings oxygen from air and carbon compounds from food to the cells, where oxygen combines with carbon to produce energy and carbon dioxide. Like burning a match, but without the flame. Then, circulating blood removes the carbon dioxide. Both birds and humans make energy the same way, but birds can make much more of it.
Birds maintain body temperatures about 10 degrees higher than ours. These higher temperatures speed up chemical reactions that produce energy. Bird hearts beat much faster than ours and pump more blood per minute to their cells. Our lungs expand and contract. We breathe fresh air in and stale air out. But there's always some stale air remaining, not very efficient.
It's one of the reasons we run out of breath when exercising. Birds don't inhale and exhale with their lungs. Instead, 9 air sacs expand and contract to pump air through their lungs. Some air sacs are located in front of the lungs. Others are located in the rear. The front sacs pump stale air out of the lungs. The rear sacs pump fresh air into the lungs. Fresh air flows past a sponge-like structure in the lungs where blood releases carbon dioxide and absorbs oxygen. Birds don't run out of breath because their lungs get a continuous supply of fresh air without any stale air remaining. Birds gulp their food whole, slightly mashed, or torn into pieces.
Most birds have a sac-like crop where they can store food before digesting it. Then their stomach starts breaking down the food. Next, it goes into their gizzard, a strong muscular bag filled with grit or stones. Birds don't have teeth, so this grit acts like teeth, breaking the food into smaller pieces. Turkey gizzards can actually bend iron bars and grind steel. Birds' intestines are much like ours. Carbon compounds are digested and enter the bloodstream where they start their journey to the cells.
Birds digest food much faster than we do, so it's quickly available for energy production. Cedar waxwings can digest berries in as little as 16 minutes. Birds may also binge eat before migration and gain as much as 50% of body weight to store energy before long flights.
To summarize, high body temperatures, efficient lungs, rapid digestion, and strong hearts provide the prodigious power that birds need to fly.
Bird skeletons are lighter and more rigid than ours because some bones are fused together and some have been eliminated. How are bird skeletons different from ours?
Here's a pigeon skeleton. Let's look at some very special bird bones. Bird bones are thin but strong, and many are hollow.
We have 7 neck vertebrae, while birds have from 13 to 25. Very useful for grooming and reaching for food.
Birds need strong, stiff backs to withstand the tremendous forces of flapping flight. These bones are shoulder blades, and these are the folded wings. These vertebrae in the upper back are fused together. These vertebrae in the lower back are also fused together, along with the pelvis and several tail bones.
The fused structures are light, strong, and stiff. Nature's perfect avian airframe.
Birds have several movable tail vertebrae, plus this bone for supporting tail feathers. Birds have a huge breastbone. This part is called a keel because it looks like a boat's keel. Birds' big flight muscles are attached to it. This low placement ensures that heavy flight muscles are near the center of gravity, essential for good flying.
In order to fly, a 150-pound person would need a keel 6 feet deep to attach really big flight muscles.
The breastbone, backbone, and fused pelvis also surround and protect the bird's vital organs. Here's a bone everyone should recognize, a wishbone. It's actually fused collarbones.
Some people think birds' knees bend backwards, but they don't. The legs of these American white pelicans are big enough to see how they actually work.
Here's a pelican leg. This is the upper leg, which is very much like ours, and this is the knee, which bends the same way as ours.
Birds' upper leg and knee are covered by feathers, and we can't see them.
This is the lower leg, the drumstick, which we can see. We have 2 bones in our lower leg. Birds have reduced the size of this bone and fused some ankle bones to the bottom. This joint is actually the ankle, not the knee. All of the foot bones are fused together with the rest of the ankle bones to make this single long bone.
It looks like a leg, but it's actually the foot.
What we call the foot is actually just toes. These toes are webbed for swimming.
Birds' legs and feet are perfect for springing upward and absorbing the shock of landings. These really great legs and feet deserve a splash of color. We've shown birds' remarkable eyesight, incredible coordination, prodigious power, and light, stiff skeletons. Now let's look at another flight essential, real wings.
These are the wing bones of an American white pelican. Let's compare it to a human arm. This is the upper arm bone, just like ours. These two are the bones of the forearm, again, just like ours. This is the wrist.
We humans have 8 bones in our wrists, but birds have only 2.
Everything out here is the hand, where there's been a tremendous fusion and reduction of bones.
We have 5 bones in our hands, but birds have fused them together to make this single bone. It looks like 2 bones, but it's actually just 1. All of the hand bones and several of the wrist bones fused together.
Birds have lost what we would consider to be our thumb and our pinky. This would correspond to what we call our first finger or index finger. This would correspond to our middle finger, and this one, the third finger.
Fused hand bones may not seem important, but combined with flight feathers, they're a spectacularly successful adaptation for flight, making birds masters of the air for over 100 million years. Birds are the only living animals with feathers. Feathers are another form of keratin, the protein that makes our hair and nails. New feathers grow inside sheaths and are called pin feathers. Why are feathers so special?
Feathers are among the most amazing structures found in nature. These feathers are called contour feathers because they give shape or contour to a bird. They're very, very light, yet incredibly strong. Wave one back and forth. Does it disrupt the feather? No, it holds its shape. That's because of its unique structure. This part of the feather is the quill, and this is the rachis. It's very strong and stiff. These are the veins, one narrow and the other wide. Each vein has hundreds of smaller structures, like branches coming from a tree trunk. Each branch is called a barb. Each barb also has many smaller branches coming from it, called barbules. The barbules have tiny microscopic hooks on them.
Feathers get disrupted by bumping into things, so birds need to fix them. They start at the bottoms of their feathers and comb them outward until all the barbs stick together again. This is called preening, and birds do it every day.
How does preening repair feathers? When a bird preens, it pulls all those barbs and barbules together, and all the little hooks attach one barb to another, kind of like Velcro. And the feather returns to a nice smooth shape.
How many barbs, barbules, and hooks does a feather have? Hundreds of thousands, maybe millions, depending on the size of the feather. How many times have you picked up one, looked at it and said, "It's just a feather," and tossed it away without any thought about its incredible structure?
Birds have thousands of feathers with several different shapes. Down feathers have a very short quill and no rachis. They have barbs and barbules, but no hooks, so they're loose and fluffy. Just what birds need to keep warm on cold mornings. Here are some other types of feathers: semi-plume, filiplume, and bristle. We give names to types of feathers, but birds don't care. They just grow whatever they need.
What we notice most about feathers is their rich and varied colors. This is a kestrel. Here's a magpie. Housefinch. Hairy woodpecker. cedar waxwing. Birds use their feathers for camouflage, to attract mates, and most importantly, to fly.
This is the wing of a duck called a mallard. Wing feathers are contour feathers, but some of them are also called flight feathers. These feathers out here are called the primary flight feathers. They attach to the hand. These feathers are called the secondary flight feathers. They attach to the forearm.
We've removed some feathers so you can see how the flight feathers are attached. Your arm would look a bit like this if you glued feathers to it. There'd be spaces between the feathers.
Birds cover those spaces with additional feathers called wing coverts. Upper wing coverts and under wing coverts to provide for a smooth flow of air both over and under the wing.
Now that you've seen wing bones and flight feathers, let's see how birds use them. These Air Force jets are thrilling to watch, but they're ponderous, clumsy flyers compared with birds. Birds are masters of flight. They soar on zephyrs, spring into flight from twigs, hover in midair, plunge after fish, land on ice, and rise in formation from lakes. How do birds fly?
Birds must overcome two forces in order to fly. The first is gravity, the force that pulls things down.
To overcome gravity, birds produce lift.
The second force is air resistance or drag. Have you ever ridden in a car and stuck your hand out the window? Remember how the wind pushes your hand back? That's drag.
To overcome drag, birds produce forward thrust. These birds are gliding with outspread wings. How do they stay aloft?
Because their wings have a special shape called an airfoil, blunt and round at the front, curved on the top and bottom, and tapering to a thin tip at the rear. As an airfoil moves forward, it cuts air into two streams, the upper stream going over the wing and the lower stream going under the wing. Air flowing over the top of the wing follows a curved path and travels faster than the air traveling across the bottom. Here's the pelican wing. Notice the wing shape, rounded and blunt in front, tapered in the back. There are bones, tendons, and muscles at the front, but only feathers in back. The feathers are curved, so the wing is also curved. A perfect airfoil. Light, strong, and efficient. Now we need a little science, something called Bernoulli's principle. Bernoulli's principle says that air pressure decreases as air speed increases. So there's less air pressure on top of the wing where air moves faster and greater pressure under the wing. This difference in pressure lifts the wing up.
You can demonstrate Bernoulli's principle yourself. Put a thin piece of tissue paper under your lower lip and blow over the top. See how the tissue comes up? You're not blowing underneath the tissue, you're blowing on top. Faster airflow causes lower air pressure and the tissue lifts. Air pressure might not seem strong enough to lift this heavy bird, but it's what lifts airplanes off the ground. A fully loaded 747 weighs nearly 1 million pounds. Now we know how birds stay aloft, but how do they produce forward thrust? How do birds use feathers as propellers?
Birds use their primary flight feathers as oscillating propellers. The leading vanes of primary flight feathers are narrow and inner vanes are wide. So as the wing goes up and down, the vanes twist like this, oscillating propeller.
Each primary is curved on top and bottom, like an airfoil, and creates lift as it travels through the air. When a primary twists on a downstroke, its top surface becomes its front surface and creates lift in a forward direction. This front-facing lift is the thrust that propels birds forward.
Let's put lift and thrust together to see how birds actually fly.
Ask how birds fly, and most people say they grab a wing full of air and push it down and back. Let's see what actually happens. The wings of this Canada goose are pointing up and just starting a downstroke. Here's the wing halfway through the downstroke. The inner wing moves down slower than the tip because it's closer to the body. It generates lift because the goose is moving forward and the wing's an airfoil. The wing tip is moving down fast. Air resistance twists the primary flight feathers and they act like propellers, driving the goose forward. Here's the bottom of the downstroke. Now the goose must complete an upstroke. Here's the wing halfway up. Momentum carries the bird forward and the inner wing continues to provide lift. The wrist bends sharply, reducing the wing's surface and air resistance, allowing the goose to raise its wings without pushing its body down. Here's the wing just before the top of the upstroke. From here, the goose will straighten its wrists and be ready for another downstroke. The goose won't need to work so hard after it reaches cruising speed and will make smaller wing movements. Birds don't fly by pushing their wings against the air. Instead, they use their primary flight feathers as propellers and their wings as airfoils. We humans didn't discover propellers and airfoils until we started building airplanes, about 100 years ago. Birds were already using them when dinosaurs still ruled the earth.
As many as 40 different muscle groups allow birds to change the shape, angle, and speed of their wings, and even move them independently. Their tails also play a big role. Birds take off, soar, pivot, slow down, and land. They fly in still air, headwinds, side winds, and tailwinds. We humans don't know how every wing movement works, and birds don't need to. They just fly.
There are many ways to learn more about birds. Bring some bread to a park and watch them eat. Get a bird feeder and learn the names of species that visit. The Peterson Field Guide can help you identify what you see. Search for birds on the internet and find many wonderful pictures and articles. You can see how birds act and listen to their songs at the Cornell Lab website. Knowing what makes a bird only increases our envy of their remarkable eyesight, incredible coordination, prodigious power, light, stiff skeletons, and amazing feathers. We're confined to earth by inefficient lungs, heavy bones, and featherless skins. But our imaginations can rise with birds, conjuring images of soaring freedom. When you see a bird, don't say, "It's just a bird," and hurry along. Instead, treat yourself to some time watching them. and let your thoughts climb on make-believe wings into the ever-beckoning sky. Imagine springing into the air or running across water while gaining speed. Flex your mighty wing muscles and flap upward. Hear the wind sing through your primary flight feathers as they thrust you forward. Find a rising current of air and soar ever upward until you disappear from earthly view, borne to distant adventures on gentle winds.